In this video, we're going to discuss what the value of K tells us, and K being the equilibrium constant. So it's the concentration of the products raised to their stoichiometric coefficients divided by the concentration of reactants raised to their stoichiometric coefficients. We're going to discuss three different scenarios where we look at K values that are much greater than 1, K values that are much smaller than 1, and K values that are approximately equal to 1. And in those three scenarios, we're going to look at the product and reactant concentrations you would expect, some conclusions about the reaction, and then provide some examples of reactions with very large, very small, or moderate equilibrium constants. Let's start with an example reaction where the equilibrium constant K is much greater than 1. If K is much greater than 1, and K is the ratio of products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients, what we know about the product and reactant concentrations is that the product concentration must be very large, and the reactant concentration must be very small, so that when we divide a large number by a small number, we still get a large K value. One of the conclusions of this is that products must be favored because the concentration of products is very large. Another way to think about this in the context of delta G is that the reaction is spontaneous in the forward direction. If at equilibrium there's a large concentration of products, we can conclude that the reaction must proceed in the forward direction spontaneously. An example of a reaction with a very large equilibrium constant is silver plus reacting with ammonia to create this silver-ammonia complex. The equilibrium constant is 1.5 times 10 to the 7th at 25 degrees Celsius. Now let's look at an example where the equilibrium constant is much smaller than 1. When the equilibrium constant is much smaller than 1, we know that the product concentration must be very small and the reactant concentration very large. So if we take the ratio of a very small number to a very large number, we get a small number. That is, the reaction equilibrium constant is much smaller than 1. Based on this, we can conclude that reactants are favored. And again, thinking about delta G, the reaction is non-spontaneous in the forward direction. An example of this type of reaction would be diatomic nitrogen reacting with diatomic oxygen to form nitrogen oxide. The equilibrium constant for this reaction is 4.3 times 10 to the negative 25th at 25 degrees Celsius. Our final scenario is when the equilibrium constant is approximately equal to 1. It's important here to point out specifically what we mean by K values close to 1. By close to 1, we mean K values that are 10 to the negative 2 all the way to 10 to the 2. So that means anywhere from 0.01 to 100 is an equilibrium constant value that is close to 1. This makes sense looking back at the equilibrium constants we've seen already in this video. We've seen equilibrium constants that are 10 to the 7th and 10 to the negative 25th. So when you're comparing 10 to the 7th or 10 to the negative 25th, 10 to the negative 2 or 10 to the 2 is pretty close to 1. What we can conclude about reactions with equilibrium constants close to 1 is that there will be significant amounts of both the products and the reactants at equilibrium. An example of this type of reaction is hydrogen gas reacting with iodine to form HI. The equilibrium constant for this reaction is 54.3, at a temperature of 430 degrees Celsius.